All right, we're live. Happy Friday, everyone. Today is March 23rd, and this is episode 37 of Get Your Tech On, our show on all things DOCSIS. I'm Brady Volpe, founder of the Volpe firm and Nimble This, the technology fan in cable. With us is John Downey, the man who built his home's foundation with UBR 10Ks instead of concrete blocks. John is also CMTS Technical Leader at Cisco Systems. Welcome back, John. Glad to have you with us.
It also serves double purposes, heating the house. There's enough heat that comes out of these things. Good to be back.
Thanks, John. Also with us is Larry Wolcott. He's a man who tamed the wild west of P&M and is technical leader at Comcast. Larry, so good to have you with us.
Thanks, Brady. Nice for the introduction, and not as exciting as John's, but I'm glad to be here. And 37, by the way, my 37th birthday is coming up, so it's very appropriate that I'm here on the show with you. Totally kidding, not 37 years old.
37. I would have guessed 30, like 27 maybe, but congratulations. So
Alex, I was dumbfounded. Sorry.
Yeah, this is gonna go down in history here. So nice, Larry. So our topic today is spectrum analysis everywhere and best practices for technicians in the field. So I mean, there's been so much with spectrum analyzers, and we've been around for so long. I think I just want to start off a little bit with sort of the evolution of spectrum analyzers and a little bit of history on it, and kind of cover, how they got here and how we've been using them. And Larry, I'd kind of like to punt this to you and just get some thoughts from you on how you've seen these evolve and what your initial thoughts are on it.
Yeah, thanks, Brady. So, to me, I'm less about the history of spectrum analyzers. They've been around for a long time, and the technology. We'll get to cover some of the gory details about how they work and all that. But more so, the transformational time for me with spectrum analyzers was when we were able to introduce them into the DOCSIS specification. And our commodity CPE stack now became a remotely controlled spectrum analyzer out in the field. That was the game changer to me, Brady. And I remember that was not quite 10 years ago, but it was 8 or 9 years ago maybe. And I remember one of the silicon vendors, I believe it was Broadcom, did a demo of their full band capture at the time. And to me, it was not that religious of a guy, but I had a religious experience at the time. I thought, wow, this is going to be the future of how we measure our systems and our performance. And lo and behold, I'll say here at Comcast, we have, we'll get to that later, but basically spectrum analyzers everywhere. And the things that people were dreaming about 10 or 15 or 20 years ago is really the reality we're living in today in terms of tools and capabilities. It's really impressive. John, how about you?
Yeah, I'm having the visibility that we do now. We never thought, we were talking about upstream spectrum analysis on the CMTS and getting viewing. And I said, man, it'd be great if we had downstream. And then we got full bandwidth capture. I'm like, whoa, now we're a totally different level of troubleshooting and visibility into what's happening in our cable plant. And then we would sit there and say, well, does that negate the use of test equipment and sweeping? Yes and no. A lot of it's complementary, and you're still going to utilize your return on investment in your test equipment. Just having more visibility just helps me troubleshoot so much easier. Be able to triangulate or target where these problems are, and then P&M on top of that. This session that we're having on spectrum analysis is actually kind of timely for me because I'm putting together a presentation on DOCSIS 3.1 upstream, and when we do OFDMA on the upstream, I don't know about other vendors, but the Cisco CMTS keeps same average power. So if the CMTS wants to see 0 dBmV, that's for the entire channel. Now, if you're doing DOCSIS 3.1 channel that's 48 megahertz wide, it's a lot wider than a 6.4 megahertz wide channel. So and I'm not talking power per hertz, I'm talking same average power. So if you take 0 dBmV on a spectrum analyzer that's this high, when you spread it out this far, it'll look this high. So you have to understand how a spectrum analyzer gives you kind of like an optical illusion, because what you're reading is just based on the resolution bandwidth filter, not the average power. So with that in mind, I'm coming to the epiphany of myself of when I start running wider upstream 3.1 channels, I'm going to get lower MER. I'm going to get, unless I tell the CMTS to jack the levels up just for the 3.1 channels. So I'm coming around full circle on really understanding the cable modem, the CMTS, and what happens when I start doing OFDMA on the upstream. And I want to run higher modulation, afford lower MER. Sorry, I'm going on a rant here, but it all comes into play with spectrum analysis.
It does. And so I'll say it's very timely for me too. I'm putting together for our local chapter here, the SCTE Rocky Mountain chapter. Next month, we're having a topic, full crash course, hands-on about spectrum analyzers. So very timely for me as well. Different reasons.
So I think it's a neat thing that's happening. We're talking about, because spectrum analyzers are now in cable modems, they give us the ability to see all of the RF signals going into just about every subscriber's home, so we can do a lot more effective troubleshooting. But what's kind of unique, all three of us are guys that have been working with spectrum analyzers probably most of our careers. We're actually finding that, as John says, it's like eye-opening. Larry, it's eye-opening. Even me, it's eye-opening. We, as sort of mature people who understand spectrum analyzers, are finding new uses for them, are learning, John, like you said, about the upstream, new ways or interesting things that we have to kind of relearn about spectrum analysis. There's kind of a challenge for new guys that are coming into the industry who have no background, no experience with spectrum analysis. Do you agree with me?
Totally, yes. I'll say, at Comcast, they're ubiquitous and everywhere, but that doesn't mean we necessarily fully understand what it all means and how to use it. So there's a lot of work to do, but I think that's a great problem to have. Imagine if we couldn't see what we could see today. We can fully analyze with our 3.0 network the readiness of our OFDM signal that's out there without having 3.1 equipment out in the field. So it's, if we didn't have that capability now, it would be completely onerous operationally to go certify a node by driving trucks around and doing sweeps. I mean, to do it the old way would completely blow up the costs. And then we'd have to, I couldn't imagine life without it now. But your point is well taken. I think it's really incumbent on us old guys, such as we are, to help bring it to the masses and improve the level of understanding out there.
So the basic technology behind spectrum analyzers has also changed, right? We started off with like a swept type of spectrum analyzer that runs through the whole band, and now what's in cable modems is what we call an FFT type of spectrum analyzer. So is there a big difference between these two types of analyzers? This technology, the fundamental technology in them?
Definitely, John.
Oh, you're saying definitely, comma, John? Were you calling Brady John, or you're saying, all right, John, take it away?
Commas matter.
When are we going to eat, Grandma?
We're going to eat Grandma?
Commas matter.
A question mark, John, yes.
To elaborate, his name is Brady. I agree. It's different. The FFT versus an analog front end, the big old heavy HP 8591C that could weigh 40, 50 pounds, lugging it around. I'm not aware, but maybe you guys know, is there any app for a smartphone, maybe with an external device, to do this on an app on a smartphone? Chipset is really small in a cable modem, right? So why wouldn't there just be like kind of like the QR reader or the swipe you put on a cable on a smartphone to do credit card transactions? Why isn't there like a little RF input device we can plug into our smartphone?
Yeah, that's funny.
And then
Yeah, you're setting me up here, John. I don't know. Should we go there, Brady?
It sure would be cool.
Yeah, that would be cool. Okay, should we go there? You wanna? Let's. You mind if I do a little screen share?
That'd be awesome.
Okay, let's do it. We're going to show off a little bit. So at Comcast, we have taken advantage of the capabilities within DOCSIS. I'm going to share this with you all. Okay, can you see it?
Yep, your screen is up.
So this is our technicians meter app. This is the iPad in my office, and it's connected to basically a DOCSIS gateway by Wi-Fi, and it functions as a a field measurement device. So there's full spectrum updating in real time. It's very fast.
And this is on your iPad? This is on an iPad we're seeing right now, right?
That's right. This is live from my iPad, and I'm touching and pinching and zooming, and it's responding the way you would expect an app to work. And let's do here. I'll do a channel scan. So we'll say we're on outlet number 3, and you can kind of get a sense. We'll talk a little bit about what this is, but Brady, I'd rather you show your spectrum analyzer. But when this loads up, we'll talk a little bit about what you're looking at.
So the technician is on their smartphone, iPad. They're on someone's Wi-Fi. Could be their cell phone, whatever. But they're logging into your system that is then polling cable modems for full bandwidth capture, or polling the CMTS itself for upstream spectrum analysis.
Absolutely,
correct?
And it's all an app. So it's this whole software world. Okay,
so if they need to troubleshoot a specific location they're standing at, they could use a cable modem at that location?
That's right. Or you could use a meter that has a plain old DOCSIS chip, and they do exist now. They've been kind of commoditized. So what you're looking at now is a single channel, the 6 megahertz occupied spectrum in the upper right-hand corner, and the the QAM performance in the constellation. And it's pretty neat. It's funny, when we first released this app for field trial, I got a call back from one of our VPs from the regions, our divisions. He said, "Larry, you won't believe this, but I sat down with my iPad, and this was the first time in 13 years that my son ever asked me about my job when he saw me using this app to do the spectrum analyzer." I thought that was funny. It was like, okay, so just because it was put into this modern context of iPad and app and technology, now all of a sudden that became interesting to this kid. So that's kind of a fun story.
Well, it's so transformative and so appropriate for the users today, and I mean the age of a lot of the techs that are coming into the industry, because this is what everyone's using for email, for gaming, for their jobs, for everything. So we all know how to use this, and it's much easier to use than a lot of things that we're doing. So the UI is awesome on this.
Yeah, very intuitive. That's right.
Larry, that downstream constellation, is that readily available from the cable modem?
It is. That's right. So most of this is just plain old DOCSIS spec, which is hilarious, except for the constellation, which is not. But if you have the SDK, and we do, it's not hard to instrument the API so that it can return the INQ values to display. But, Brady, I'm going to stop sharing. I don't want to steal the show here. Let's get back to the agenda. But John set me up for that.
Yeah, that's a pretty cool demo, though. It's a good question from John.
Yeah, we're really proud of that. And we have about 20,000 technicians here at Comcast using that every single day. It's fantastic.
Yeah. And so what I have behind me here is what you would normally see. This is an AT2500. It's a normal spectrum analyzer, and I can just show kind of a comparison of what you just showed, Larry, with the spectrum analyzer. I'm just showing a screen view of that same box that I showed behind me. But that box is a much more expensive piece of hardware. John, as you said, it weighs, I don't know, 10 pounds, or and it does have a battery, but has a limited battery life. You can log into it remotely, but it requires an Ethernet cable connected to it. And now we're seeing a spectrum analyzer trace of kind of similar to what Larry showed on his app. It's just a little bit different, and we can change the span on this. So now we can go down to a smaller bandwidth, so we can actually see the QAM channels. I'll change, something that a lot of people may not understand is something called resolution bandwidth, John, as you had indicated. So what resolution bandwidth does is it's kind of like changing the filtering on the front end of the spectrum analyzer. So right now we have a resolution bandwidth of 100 kilohertz or 1,000 kilohertz or 1 megahertz. And effectively, that's like having a 1 megahertz filter on the front end of the spectrum analyzer. And that limits the resolution or effectively how narrow of signals that we can see. We'll see as we drop the resolution bandwidth down to 300 kilohertz, that's putting a smaller filter. And as that filter scans across, now you can see we're able to see we have more resolution. We can see more clearly that there is a notch in between these two QAM channels. So this is a 6 megahertz QAM channel. If we drop that resolution bandwidth even smaller to 30 kilohertz, now we see there's suddenly a lot more noise on this QAM channel. I say, well, why is there more noise on here when I drop my resolution bandwidth of 30 kilohertz? And again, what we've done is we've put a smaller filter in front of this whole analyzer, so we're able to see the noise. Again, we can drop it to 10 kilohertz, and it's going to get even more noisier. And you notice that the level dropped. So, John, this goes back with what you talked about earlier, about how changing the resolution bandwidth changes the actual power, because we're narrowing the filter, we're reducing the amount of RF spectrum that we're integrating over, and we're also able to see even more noise in here. One thing I always like to
I'd be careful. I'll be careful with the term noise. Maybe it's semantics, but
yeah, that's
I would just say granularity. The QAM channels are amplitude modulated, right? Quadrature amplitude modulation. So you're just seeing the amplitude modulation.
Correct.
Let's not call it noise, right?
Yeah, this is actual data. You're absolutely correct. It's not noise. This is the actual data that we're seeing on top of these QAM channels. And one thing I've often told people that are using spectrum analyzers would say, well, it's really noisy on top of this QAM channel. It's really difficult to get an accurate measurement on top of this QAM channel. I always tell people you can turn on averaging in these spectrum analyzers. And when you turn on averaging, now everything calms down. So you can get a more accurate measurement when you're trying to measure the QAM channels, say if you put a vertical marker on there.
Also, some people just do heavy video bandwidth filtering.
Yeah, there's a video bandwidth filter that does a similar thing there. So if we turn off averaging or go back on the peak there, we can put on the video bandwidth filtering. It doesn't do quite the same job as video averaging, maybe with a little less resolution bandwidth, we'll see it, but averaging does normally a better job.
Yeah, I see a lot of misunderstanding about resolution bandwidth. That's a great point, John. And we have to answer those questions a lot in the field. And what it really means is if you look up really close at the signal, and it's a bin, and there's basically a chunk of spectrum, a bandwidth, and then all of the power that's summed within that band. So if you're looking at 300 kilohertz resolution bandwidth, you have a 300 kilohertz chunk of spectrum, and it's summing all of the power and putting it into a single bin. And the smaller that slice of spectrum is, the more resolution you have. And the closer resolution you get to the symbol, the more you see the actual signal vector. So it looks like noise, but it's just, that's what the signal looks like. But on a wider resolution bandwidth, you get a quantization effect that essentially averages several of the vectors and puts them, makes them look a little smoother. So that's kind of the effect of resolution bandwidth versus that noisy look. We get that all the time. And the other thing that's really, really important and often misunderstood is the power levels. When you're looking at the power level in raw spectrum, and it's not, let me rephrase that. We're used to seeing power levels measured for a 6 megahertz channel, and that's not the same as the actual power per bin. So the little slice of 300 kilohertz, That's the power of that within that little chunk of 300. Whereas if you're looking at the power level of a DOCSIS channel, that's all of those 300 kilohertz bins summed together within the channel. That's the total channel power. And guys will look at folks will look at a spectrum analyzer and see a very different power measurement, in dBMV relative to what they're used to seeing in, for example, their tools that show them DOCSIS power levels and not understand that. So we get that all the time.
Yeah, and there is a lot of literature out there that and now actually you just Google it that tells you how you can do the conversion from one resolution bandwidth to another, or from say one DOCSIS channel bandwidth. If you are working in a 6 megahertz world and now you start going into an OFDM world where the bandwidth is much larger, it's an easy way to mathematically convert from say 6 megahertz to 96 megahertz. It's using a log ratio to do this, but the math is pretty simple to do using a calculator. And so you can Google these formulas to do that conversion.
Yeah, a great point. But before you can even Google that, you have to understand why. And a lot of folks just don't understand. They were trained that power is channel power, not spectral power or resolution power. So it usually takes a little bit of education, but people, once they figure it out, I think it helps normalize how they think about spectrum analyzers.
But I think that the important takeaway is anytime someone gives you a measurement from a spectrum analyzer, always ask, hey, what's the resolution bandwidth that measurement was made in? Because it's very important to understand that.
Yeah, I mean, if you're worried about accurate levels, then you definitely have to take that into account. If you're just looking at a spectrum analyzer to get vision, carrier to noise ratio, it's just a peak-to-peak measurement. Looking at a single carrier QAM versus a old analog channel, basically if it's 6 dB, that might not be accurate because the spectrum analyzer will show all the power under the video carrier at the video carrier frequency of an analog channel, because the video is amplitude modulated. It doesn't have a lot of width.
And it's very narrow.
Yeah, and the QAM, you have to use a correction factor, 10 times the log of 6 divided by 0.3. So whatever power reading I got for 300 kilohertz, you add 10 times the log of 6 divided by 0.3. Some people might say 5.4 divided by 0.3 because that's a symbol rate, versus the channel width of it's pretty close. But either way, usually you use test equipment to do accurate level measurements, not really a spectrum analyzer. What I wanted to ask Larry is, and I see this, is how quick can a cable modem report fast rise time noise, impulse noise?
Great question. And I think on our agenda is to talk about, we love the ability to use CPE spectrum analyzers, but they do have shortcomings. They aren't the same. These things are $25,000 for a reason. And one of the limitations is speed. And while it does look pretty quick when you're seeing it update on my screen, it does not necessarily, well, it doesn't even compete with like an AT2500 or a Q, for example. Fast rise time, burst noise, sometimes you can't even see it, and you have to rely on the demodulators, coding. The good news is we have two other tools to help us see it, and the days of staring at a spectrum analyzer to interpret are becoming part of the past. And then if you look at, I won't bring it up now, but most of the tools, while you do have a spectrum view, all of the material statistics are also there overlaid so that in real time you can see the MER, you can see the code word performance, you can see the uncorrectable error rates, you can see, the LDPC statistics and all that stuff that you care about in real time, so that you don't have to visually say, oh, whoa, I saw that burst, I know what it is now. So there's other ways to get around that, but fair enough, they're not as fast. That's their day job is to demod, and they do that real good and deliver great service over DOCSIS. But we're just getting this spectrum analyzer business as a side effect, and we're still happy with it.
No, I agree. The spectrum analyzer itself is one tool in the toolkit, right? And I've always said you never rely on a spectrum analyzer for the gospel of the whole thing. You look at per modem MER, per modem correctable, uncorrectable effect, per upstream correctable, uncorrectable effect. Because the spectrum analyzer, frequency versus amplitude, you're not going to see group delay. You might see micro reflections, standing wave, but you're not going to see issues. I've even told people you got a perfectly clean plant, carrier noise is great, spectrum analyzer looks great, but maybe the modem's timing is bad. Tools to look at: the flap list, MER, uncorrectable FEC. If I notice uncorrectable FEC is incrementing more than correctable, I usually point towards impulse noise. Because if it was additive white Gaussian noise, then correctable FEC would increment as well.
That's right. And you'll see that reflected in MER, be fairly consistent. So you're right, all great tools. Brady, what other limitations would you say that using commodity spectrum analyzers might have against traditional stuff?
Yeah, I mean, I think the biggest thing we see right now for a lot of them is they're not quite as fast, so we do miss impulse noise. And depending on the make and model of the cable modem, some of them don't have quite the same dynamic range as what you'd get with a spectrum analyzer. So you miss out. You're not going to be able to measure your composite triple beat or your CSO or CCNR if it's all QAM plant. Meaning you're not going to be able to see as low in your noise floor. But again, we're not trying to look at some of those type of impairments with a cable modem. We're not trying to do the same level of measurements with a cable modem. We're looking for more coarse measurements, like, is there a big suck out in the plant, or is there a big standing wave on the plant that's going to cause the subscriber to not be able to demodulate a channel, to actually not be able to see a channel? Or this would explain why they're getting pixelization or macro blocking on one of their channels and call in and complain, and eventually result in a truck being rolled to that subscriber's home.
Yeah, great point. Brady, would you mind bringing up your spectrum analyzer and explaining to everybody what the dynamic range means and the sensitivity?
Sure, I can. Let me just share that again. You want the AT2500 brought back up, right?
Sure, yeah.
Yeah,
that's a great point, and something we should probably just touch on.
So I think that should be shared now. So what dynamic range is, starting off with that, would basically be an indicator from, are you able to see my mouse moving on here?
Yep.
So dynamic range would be, say, the ability to tell you that the peak of this is an analog, this is probably a pilot tone here, either for an AGC, an analog gain control and an amplifier, or just a reference tone here. But it would tell us, like, the dynamic range is what the delta is from the top of this pilot tone to the noise floor. And right here we have 10, 20, 30, 40, almost 55 dB of dynamic range. Depending on the cable modem, you may have 55 dB of dynamic range. Now, this spectrum analyzer is capable of much, much more than even 55 dB of dynamic range. It can go much higher than that. Depending on the cable modem, we may not see that. I can pull up a cable modem here and give kind of an example we'll look at what we see from a cable modem. Here's a suck out. Let me just pull a suck out here. So on a cable modem here, we're seeing like and this is a live response from a cable modem, a full band capture cable modem. We can see the noise floor here. We're seeing 10, 20, 30, 40. So we're getting just about 45 dB. That's the maximum that we can see on this cable modem of dynamic range, meaning the peak of what we see on the QAM carrier here to the noise floor is 45 dB. That's the maximum delta from dynamic range. Comparing that back to the sunrise here, we're getting 10, 20, 30, 40, 55 on this. But again, as I said, this AT2500 can do much, much more than that. But the best we're going to get on this cable modem is about 55. So is that?
And the spectrum analyzer has an internal amp as well, right?
Yeah, This spectrum analyzer has an internal amp. Right now, we have the attenuation set to 0. I have fairly low signal levels coming in because in my lab. I'm splitting the signal multiple ways to feed other devices, so it's capable of way more than what we're currently showing. So that's on dynamic range.
one, you're trying to say, well, what is the limitation of, say, a commodity device like a cable modem with spectrum analyzer versus, a higher price spectrum analyzer? What about the other way around? A spectrum analyzer just shows, say here, amplitude versus frequency in this screen. The downstream is always on. What if you have two downstreams overlapping? You can't really see it on a spectrum analyzer. But with the cable modem side, you could do ingress under the carrier. If there is a feature like that. I know some test equipment have that feature, ingress under the carrier. But like Larry mentioned, you could look at correctable, uncorrectable FEC. MER would be really bad. But from a typical spectrum analyzer, you might just see amplitude and it looks fine. Yeah. If they're both the same level, it might add in phase at 3 dB.
Yeah. And the benefit is with the $35 cable modem that's sitting in the subscriber's home 24/7. What we're showing here is that we're able to see that there's both there's a standing wave and there's a little bit of a suck out on this cable modem. It would be expensive to run around to every single subscriber's home with an AT2500 and look for this type of signature. Whereas with an inexpensive cable modem and the full band capture capability, we can identify these things just by running a background process 24 hours a day. So that's kind of the cool functionality with a cable modem. So there's pros and cons of both.
That's right. Should we talk a little bit about the techniques for seeing ingress under the carrier and error vector spectrum and things like that? Is that worth, or is it a little too technical?
I think there's benefits to it because there's reasons. So like with this, the spectrum analyzer that I was showing, it's really hard to know if there's an impairment under that QAM channel. So with a cable modem, being able to know that there's an impairment under a QAM channel, there's some value to that.
Indeed, there is, Brady. So first, before I go off topic from the spectrum, your example of your Spectra tool, that's a great name, by the way. I love that.
I know the guy that came up with that, so he was very smart.
It reminds me of a superhero. The thing that we see at Comcast, and this has generally been pretty anecdotal out in the field, but it's true, is you see a lot of things happen due to the environmental influence on the network, right? So the sun hits the plant, it gets cold, it rains, it snows, the wind blows. These are the things that change the physical properties of our network, in particular the impedance characteristics, and what we'll see is literally 5 times a day we'll see a suck out or a notch or a standing wave come and go as it's responding to the environment. And now, even if you did have a really rigorous preventative maintenance program and you drove trucks around on a schedule once a month, you would never catch these things. It'd be impossible because you don't have the measurement resolution of being there at the right time in the right place in the network. And we can see those today. We can correlate them. We're using machine learning and AI to predict weather patterns, for example. And a lot of times there are certain things, suckouts are a great example, where we can predict along with the weather when customers are going to lose service and why. And so now we can prioritize proactively repairing the plant so that before the thing that causes this suck out or otherwise spectrum anomaly to impact these customers, we can address that proactively. So that's exciting. But back to seeing the interference under the carrier. There's a couple of techniques to do that, and there's lots of clever ways. And the easiest by far is just to look at use the demodulators if you have them available. For example, in DOCSIS channels, you do. So you can use the demodulators to tell you the code word statistics or the MER, and you'll get a pretty good sense about what's going on there. You can do carrier to interference noise ratio calculations and things like that, and we have a lot of success at Comcast doing that. But the dilemma is when you're in a place in spectrum that you don't have a tuner available to you, right? So the spectrum capture doesn't have the capability of giving you an MER value. The tuners do that. And your tuners are fully occupied having their DOCSIS lock. So there are some techniques for mathematically removing the intended spectrum and then leaving the spectrum that's there, but they just don't have, they have limited effect and capabilities. Would you guys like to talk a little bit about what you know in that space?
So, John, yeah, you have any background on that, or you want me to?
I want you to tackle it first.
Okay. So, on the full band capture side for, now I lost my place, John. Larry, we're doing ingress under QAM still?
Yeah, well, yeah, ingress under QAM, we were just talking about that a little bit.
Yes. So I'm just blanking.
All right, I got it. So no, it's fine. So basically, if you have a demodulator there, it's pretty easy. And if you don't, you're going to have limited success. But you can, there's some math tricks you can do to, for example, if you've taken a reference of the spectrum, at the node, then you can, flatten the spectrum out, and you can mathematically remove what you think should be there. And in some cases, in particular, in between the QAMs, you can see some hints. It works okay, but not great. The place that does work really good is if you've got a demodulator that's giving you statistics. And one technique that I've seen in at least one of the vendors, if not more, they call it error vector spectrum. They basically use the forward equalizers with the averaging turned off, so that it allows them to get the characteristic of the channel reacting to the interference within the channel. So instead of, when you have averaging turned on in the downstream equalizer, it does a great job at characterizing the channel, so flatness and notches and things like that. If you turn off averaging, it allows the equalizer to respond to the interference within the channel, and you can use that as the error vector to mathematically remove the known signal and show you the noise underneath it.
So this is doing the using the post equalizer in the cable modem and looking at the post equalizer kind of in a similar way to what we do with the pre equalizer in the upstream, but we take the coefficients from the post equalizer and extract the in-channel frequency response that's driving, and then underlay that underneath the QAM channel. The post equalizer response is giving us basically how the post equalizer is working to correct for the impairments that it's seeing from the that is correcting for when the cable modem is demodulating the QAM channel, and those coefficients from the post equalizer are then showing us basically the garbage that's underneath there.
Exactly. And the forward equalizer, the blind forward equalizers and the downstream tuners are very different than the adaptive pre-equalizers. They're very fast, they respond quickly, and if you turn off averaging, you can see a pretty good picture of what the noise signature looks like.
Right. There's also in the post equalizer a number of equalization blocks that are in there for correcting or actually removing some of the, if you get like coherent interferes underneath a QAM channel, so you can extract that data as well to identify any coherent interferes, like if you get a single tone or some small tones underneath there. So those can also be used to say, hey, I've got some individual singular tones that are underneath, like if you had pagers aren't that are around that much anymore, but if you had like a airplane transmitting that gets in, or some other type of tower that's transmitting to airplanes, something like that, in the 400 megahertz band, LTE in the 600 or 700 megahertz band. Those can be utilized to identify specific frequencies that are under a QAM channel as well.
Yeah, great point, Brady.
So, yeah, absolutely, very good point to bring up, Larry, that things that a normal spectrum analyzer, like we talked about the swept response spectrum analyzer, would absolutely be invisible to, we can use these post-equalization capabilities to be able to identify. I think something I want to throw back at you is one of the challenges we've had is a lot of cable modems we're not able to get the post-equalizer response to because the MIBs haven't been standardized on.
Oh, you're such a rascal, Brady. You're setting me up again. Okay, so let's talk about that. That's and part. I'm glad you said that, because that's been one of these adventures we've been on for many years. Is like we standardized with P&M to get the adaptive equalizers all sorted out. We're doing the same thing right now. with Cable Labs to do it. We've got approved a downstream EC, an EC to standardize the downstream equalizer coefficients. We also have an SCTE, and a Network Operations Subcommittee number 7 for proactive network maintenance. We're putting together a whole application notes on how this all works, so folks can implement them, whether it be in your OSS tools within your operations, or if you're a tool vendor, if you want to add that kind of a capability to your tools if you don't already have them. Kind of a standards-based way to do that so that we can all see and say the same things about what's happening in the channel.
Yeah, and I want to commend you on that, Larry, because you've really been driving that initiative on getting the post equalizer taps in the cable modem standardized, and also all your work on the SCTE and with Cable Labs. So thank you very much on behalf of the whole industry for driving these initiatives.
Oh, you're such a smoozer. Thank you, Brady. That's nice of you. I'll say I am really excited about some of those developments. In particular, there's been some FCC changes. It's a little arcane. A lot of people don't really know about, but we could potentially use these capabilities to do, SCTE Schedule 40 proof of performance, for example. And I'm all about automation and taking advantage of the tools and technology to improve how we do business.
So how do you see that impacting the field operations? Like, I mean, especially from an FCC standpoint, when we have to start rolling this out, because from all the things that we can automate, does this change how we can efficiencies in the field?
Yeah, it does, and we've actually been able to accommodate that within some of the FCC guidelines, and it's not the way we do proof of performance in the future could very well change because of this kind of work, so that we could basically do an end of line at the end of every line analysis dump of using the forward equalizer coefficients, and just produce a report anytime, any day that would clearly satisfy proof of performance for certain aspects of Schedule 40. So we're pretty excited about that, and that's operationally, we would much rather have our technicians driving around taking care of our customers, than if we know we're good, than having them take measurements to satisfy a report.
So John, last time we talked a lot about orchestration. Do you see this type of testing actually moving into equipment that say you guys make, that we can start even expanding the scope of what we're doing? So from that standpoint,
I didn't really think about the FCC side. The FCC spec was always based on analog channels. Then we went to digital, and some of it didn't really coincide with digital channels. The only thing that really was relevant was leakage. RF is RF. I don't care if it's analog or digital, right? It's leakage. So, Larry, going back to you, I imagine that, FCC, Ron Rannick is involved a lot also. There are specs for sort of quality of service, quality of experience, end of line digital levels now and stuff like that. They are much more robust than old analog used to be. It's either on or it's not, right? It's either tiling video or it's not. But we could use an SDN orchestration app to do any of the RF stuff. But what about for leakage? Is there anything in regards to leakage that we could correlate with cable modem responses? I mean, you can obviously find micro reflections, group delay, I think that's one of the ones that we're definitely not going to replace, because we still have to do a flyover or something like that.
Yeah, great point and topic. So there's this thing called antenna reciprocity, and I spent a lot of time with Ron on this, and we've done a bunch of field trials and demonstrated it all works. Basically, it states that the gain and radiation pattern of an antenna is the same on transmit as it is receive. And that's a little bit obscure to talk about, but the reason we care about that is basically if you have signal getting out at exactly the same gain and antenna and radiation pattern, you have signal getting in. So one technique that we're using here that's very, very effective for, think about it as reverse leak detection, is using FM band ingress detection. And because FM and aeronautical band are so close in spectrum, it's only 10 or 20 megahertz away, they tend to correlate very highly. It's in the 90 percentile from what we've seen. Generally, when we use these spectrum analyzers and with this ubiquitous FM transmitters just about everywhere, unless you're way the heck out in the country someplace, and even then you still may have some, wherever we can see FM ingress getting in at the CPE, very, very strong likelihood that that you have signal getting out at the same place within the aeronautical band. So we've been able to take advantage of that proactively, but that doesn't change the state of affairs with the FCC wanting to know what's getting out. Just because we don't necessarily have CPE and cable modems that have spectrum analyzers everywhere on our plant where we could detect egress by using ingress. So it's very helpful to us operationally, but it doesn't satisfy any FCC requirements, unfortunately.
What if your CPE goes to 85 megahertz upstream?
I'm sorry, say that.
I guess you could still pick it. So what if your CPE goes to 85 megahertz upstream, which I know Comcast is doing in some cases. So your cutoff is like 102 or 105 on the cable modem itself. So you might be able to pick up FM from 105 to 108, right? Because the FM now will be in the no man's land of the duplex filter.
Yeah, no man's land is a good way to put it. No, that's true. It's true, and that said, we still at Comcast, and I'll jump ahead a little bit just because the clock is ticking. The last time I checked, I think there's 36 million spectrum analyzers on Comcast footprint. So if you think about that, very, very few of those are mid-split or operating in that kind of a configuration. So I'm going to get a lot of mileage out of those 36 million spectrum analyzers out in the field.
Yeah, so that's interesting numbers, and we're seeing about 50 majority of our customers just within, I would say, the last year went from very small percentage to getting close to 50% or more of their cable modems are supporting full band capture capability. And a big feature that came in, or I guess a big capability that made that happen was one of the major vendors out there released a firmware upgrade actually quite some time ago, which I think, Larry, you were also quite instrumental in, that made their modems support, a lot of their legacy modems support full band capture in their DOCSIS 3 modems. And that was a huge, huge benefit to everybody.
That's right. So I'll say that one particular firmware, I remember that distinctly. They turned that on and it was 8.5 million devices showed up overnight with that firmware release. And needless to say, think about it from the vendor's perspective. You're really focused on your new products, and we've already sunk the investment on and made the purchase on these. So it wasn't a real treat for them to go back and spend a bunch of time and energy and money adding new features that weren't product related or didn't add to additional revenue. So I'm really thankful for a partnership with our vendors and CPE teams to value that operationally. And I'll say it is paid back in spades every single day from the capabilities it brings to our operations folks out in the field. We're very grateful for that.
Yeah, it's hugely, hugely beneficial. So really appreciative to the vendor.
I assume that's only an 8 country.
You broke up there, John.
Oh, I assume that's full bandwidth capture is only possible on modems that have greater than 8 channel downstream capability. You're probably talking gateways, 24 downstream, 16 downstream.
It depends on the vendor and the combination of silicon that they used. So I'll say I have, like our field meter here is really just a 4x8 a Puma 5 of all things, a very old chip, but the magic is in the tuner, not the DOCSIS chip itself. So, but it depends, and there's other vendors have fully integrated solutions where the whole SoC is, basically, so there's various permutations of capabilities out there. Yeah. The good news is almost everything you buy now has it. I don't think you'd be hard pressed to buy a DOCSIS device that doesn't support spectrum capture.
Yeah, and every DOCSIS 3.1 modem will support it as well.
Yes, maybe a good segue. We should move on to 3.1 in the new world of P&M and spectrum analysis.
Yes, absolutely. So I think what I've seen with 3.1 modems, they still support the old SNMP query, but you get, if you use the TFTP, trivial file transfer protocol, to get back the full band captured data, it comes back so much faster, and then you process it from there. Also, the dynamic range seems to be, so I mentioned the dynamic range earlier, the dynamic range seems to be dramatically improved in DOCSIS 3.1 modems. Everything seems to be a little bit better in 3.1 modems.
I would agree. And so in addition to the dynamic range and the performance, and this is all basically lessons learned from what we did in, P&M 2.0 and 3.0, such as we'll call it. I think to me, the real secret sauce and the most exciting thing about the 3.1 is that we're also able to get INQ out versus amplitude only data.
We get the constellation.
Yes. So we actually get the true signal vector out of the equipment instead of basically the vector sum or the magnitude only data that we see on a spectrum analyzer. And the reason that's important is once you get this true signal vector, that's where the magic happens in the digital signal processing. So you can do complex division and multiplication and convolutions and all of this great stuff, like calculating noise under the carrier, for example, and all of the error vectors. The possibilities are so much more interesting than magnitude-only spectrum data. That's what I'm most excited about.
So the constellation itself is like almost meaningless anymore, right? Who really looks at a constellation and say, "Oh, yeah, that looks good"? It's so dense now with 1K QAM, 4K QAM. I used to look at a constellation, 64 QAM, it's easy to look at. You look if it's symmetrical, nice and square, and then you look at each individual quadrant and you look to make sure all the bits are falling where they should. But I see your point is you're getting the information that would make a constellation, even though the constellation itself, most people wouldn't know what to do with it, but the information itself, you could run complex mathematics to figure out other information like ingress into the carrier or things of that nature.
Absolutely. Staring at a constellation to me is not that interesting, like you said. Looking at like phase shifts and those donut patterns or whatever, not interesting at all. But the magic of automating that using digital signal processing, once we have in phase and quadrature information, it's the game changer to us. So one of the key features, we spend a lot of time chasing upstream noise in our cable systems. I hear figures of 85% or more is basically, chasing upstream noise. And one of the key features we've embedded in the 3.1 specification for proactive network maintenance is the ability to capture a symbol at the cable modem and the symbol at the CMTS at exactly the same time. And the reason that we really like that is because now it's not just the spectrum data where you have to look at it, go out and start pulling pads and disconnecting drops to figure out where it's coming from. You can use math to basically de-integrate the signal and see what the noise signature is coming out of every single house. And that, to me, is kind of the holy grail for operational efficiency and improving how we do stuff in cable.
Yeah, so basically, once that capability is finalized in both the CMTS and the cable modems, we should have the ability to pinpoint exactly what house is having a problem or is the source of noise, and go to that house, fix the noise, and say, job done.
Wow, that's big. When we talked about the spectrum analysis capability in the modem itself, we could do the same thing, but you had to pull every single modem to find out where the noise is coming from. You're talking about being even more proactive, and the CMTS has that information already. So even if you're talking about DOCSIS 3.1 modems specifically, right? So I see it twofold, right? There should be an upstream spectrum analysis capability at the modem itself, and what you're talking about, right, Larry? Which is different from that.
Yeah, that it's all of that. The short answer. But the real trouble with all of this stuff is that when you're talking about 3.1 only, and we're coexisting with 3.0 modems, and we will be for a long, long time. Unless you happen to have that capability in the place where the noise is getting in, you're not going to find it. So we're still going to be doing things the old way for a long time until we're fully transitioned and have this capability. More. It's too sparse right now. It'll be years before it's really, really effective, but it's taking us in the right direction.
Yeah, it's a migration.
So.
So just a few minutes left. Any thoughts on full duplex? Well, you kind of jumping in 3.1 to full duplex, but how does full duplex play into this? Will we be able to use spectrum analysis to look at full duplex signals?
Yes, you will. Good question, Brady. But things get so much. Some things get easier, and some things get just a heck of a lot harder. And if you think about the way full duplex works, one of the biggest challenges we have with spectrum analysis right now is maintaining reasonable power levels at the input of the front end. It's really easy to clip or saturate the front end of these fairly simple and low-cost devices. They don't have all the filtering and goodness that you would in an expensive piece of equipment. And I'm not exactly sure how we're going to do that with full duplex because of the way that it works. So it remains to be seen.
Yep.
I have full duplex right now in my lab in RTP, and we're looking at it right now. And I hooked up an old 8591C spectrum analyzer, and you definitely see the downstream because it's always on, but when the upstream's transmitting, I can't see it because it's underneath the downstream signal. That's the whole point of the echo cancellation, is to make the cable modems and the node and everything else work properly so it can decode. But now I need a spectrum analyzer with echo cancellation. How do I separate that signal in downstream and upstream? It's at the same exact frequency. So yeah, it can. It's more layered. The other thing I wanted to point out with DOCSIS 3.1, and I think I've done the math incorrectly years ago. Replacing a 3.0 modem with a 3.1 modem, how much gain or level do you gain from that? And it's actually more than I originally thought. It's like 8 dB. If I'm doing 4-channel upstream bonding, 64 QAM with DOCSIS 3.0, the max output is 51 per channel. Power on that'd be 51.6 is 57 dBmV. Well, if I do a 3.1 modem, its max output total power is 65. So technically, if I were to do an apples to apples comparison, and you put a 3.1 modem in a location listed, it can overcome a lot more loss than the 3.0 modem could. Now, granted, you have to allocate that power for maybe more spectrum when you turn it on. That's part of the key, right? Once I go from 4-channel upstream bonding to 16, equivalent of 16 channels, OFDMA, because I might be doing 100 megahertz of upstream, but the power is there. So the good news is I was always concerned that when I went 204 megahertz and FDX, how are we going to deal with the upstream level issue? We're already maxed out with DOCSIS 3.0. So if I start going, from 42 megahertz to 85 to 204 megahertz, I either have to get rid of all my coax and go deeper fiber with remote PHY, or I got to figure out how to have some type of extra gain. Well, one, the cable modems do have a little bit more power. Two, I am getting coax a little bit less. I'm going fiber deeper. So I have some band-aids and fixes so I can overcome some of that loss. And then hopefully the temperature fluctuation at 204, with less coax, it might be a couple dB. So I do have some wiggle room, my CMTS. That's my soapbox.
Well said. Well said, John.
So 3.1 modems go to 11 then. That's you guys.
The full story, come back at 11.
Yes. All right, guys. So we are at the top of the hour. We could, I think, keep talking on this on and on and on. But John and Larry, I want to thank you so much for your time today. This was a great episode. Any closing thoughts you want to have? Otherwise, I'm going to wrap it up. All right. So our next episode is going to be on MacFi. It's going to be with Jeff Finkelstein of Cox Communications in a month. We do our best to bring our audience great technical content every month. You can watch us on air, catch our live recorded episodes on YouTube, on volpfirm.com/events, or download our audio-only version with your favorite podcaster. If you've enjoyed this webcast, please do hit the subscribe button so that you never miss an episode. Thanks so much for being here, and we'll see you next month. John and Larry, thank you so much for your time. Take care. Bye-bye.
Thanks, Brady. Bye now.
It's a pleasure. Good talk.